Hello, everyone. So today we're going to have another seminar, high energy theory seminar on with the title Horizon Algebras and Soft Quantum Information. Daine Danielson is visiting us from Harvard/MIT. He's done a lot of work on, well, he will tell you all about it, actually. Please, Daine. He'll be here tomorrow as well. So he's staying in the speaker visitor office today. Tomorrow we'll have another room, 398, I believe. So you could talk to him.
Great.
Please.
Yeah, well, thanks very much, Nima, for having me. I got to explore campus a little bit yesterday evening. It's really beautiful here. I've never been here before. So thanks. So yeah, so I'm going to tell you about some work done with Gautam Chandran to do with information, well, to do with decoherence and entanglement outside of black holes, which will then which ultimately leads into some discussion of the information content of extremely soft modes in quantum field theory, and which, surprisingly perhaps gives rise to some new insights into quantum information theory, even outside the realm of just considering these ultra soft modes. But, I think that rather than talk at in generalities, I'll start with something more specific. I'll give you a thought experiment to think about, which is, imagine we're in the space-time outside of a cold, dead star, and there's some experimenter, Alice, in the distant past has created a spatial superposition of some body with mass. So this is a space-time diagram, and Alice is coming in from the past with her superposition. And later, as she enters this diamond dotted region here, Alice is going to attempt an interference experiment between the branches of her massive superposition. So here her superposition her mass is in a superposition of being either here or here. And inside this diamond, she's going to bring the superposition back together and look for interference between the branches. If she sees a failure of interference between the branches, then she can conclude that there's been some decoherence that's occurred to her superposition. And that's what she's going to try to do. Is determine whether or not there's been some decoherence. As long as she does the experiment adiabatically, then she should be able to minimize the amount of gravitational radiation that she emits to null infinity. I mean, of course, in the process of bringing together the two trajectories of her particle, she has to accelerate them. So there's going to be some radiation emitted, but she can, by doing things very slowly, she can suppress the amount of radiation emitted to an arbitrarily small amount. And in doing so, she can maintain the coherence of her superposition. Okay, so the question is that I'll pose to you is, what would be the difference if instead of a cold, dead star outside of Alice's lab, you replace that with a black hole outside of her lab? And well, the answer is, well, a priori, you might think that nothing would change. I mean, outside of a cold star, the metric is exterior Schwarzschild. Outside of a black hole, the metric is exterior Schwarzschild. So why would anything be any different? But from causality, you can conclude actually that things ought to be different outside of a black hole. And part of this talk is going to be to explore why it is that these stories are different. But just from causality alone, I can argue that outside of a black hole, Alice's coherence must be degraded by an amount that's much larger than would be the case outside of the cold dead star. And that's made most clear just by looking at this space-time diagram here, where I've kind of compactified the outside of the black hole. So this is out at infinity here, but the important part is it's a space-time diagram and 45 degrees angles are at the speed of light. And this is the event horizon of the black hole. And you can imagine that inside the black hole, there might be some other experimenter, Bob. And Bob could, Bob is sitting in the superposed Newtonian field of Alice's superposition, right? Alice's particle is in a spatial superposition here. And you look to the future of that, and you see that, here in this era, there's a stationary superposition. Then Bob is going to see a stationary superposed Newtonian field where he's sitting over here. Now, Bob could try to measure the superposed Newtonian field by, for example, releasing a test particle, a test mass from a trap. And that test mass would go into a superposition of trajectories, depending on which Newtonian field it's interacting with. And in that process, Bob's test mass would become entangled with which path Alice's particle is on. Is that clear so far? So he's just going to release a particle, look at his Newtonian field, and then by virtue of that, learn some which path information about Alice. Good. This gives rise to a paradox. Because if Bob is able to measure the Newtonian field due to Alice's superposition, then Alice must be decohered by a commensurate amount. If I get which path information about you, then you need to be decohered. But Bob is behind an event horizon. So whether or not he releases the particle shouldn't be able to affect the outcome of Alice's interference experiment. Because I told you Alice is going to look for signs of decoherence. And if she sees decoherence, well, then she might blame Bob for decohering her particle. But that can't be right because Bob is behind an event horizon. And so nothing Bob does should be able to affect the coherence of Alice's superposition. So the paradox is between kind of quantum complementarity, the idea that if Bob makes his observation, then Alice must be decohered by a commensurate amount, on the one hand, the complementarity, and causality on the other hand. Yeah.
So why is this causality? I mean, you might say that they're both coupled to some entangled space, some degrees of freedom in the background of space-time.
Right.
So they're started entangled. That's why.
Good. So, well, the point is that Bob could choose, that's a good point. Bob could choose to not release or to release his particle. So if he doesn't release it, then he doesn't become entangled with Alice. So, but if he does release it, then Alice had better be decohered by an amount that's consistent with his observation. I'll resolve.
Sorry,
Yeah, go ahead.
Sorry to push.
Please.
But let's say we share an EPR pair and we go light years away. Then
Yes.
I choose to perform a measurement on my qubit or
Right,
not.
right,
And then
right.
that will affect whether your qubit, something happens. So would you say this is a violation of causality?
No, because in the standard EPR type experiment, there's no way for you to tell whether you're decohered. Like, you might be in a mixed state, you might be in a pure state, but the probabilities of the outcomes are the same for either of the EPR partners. It's in this case, the probability, the outcome of Alice's measurement is sensitive to whether or not she's maintained coherence. That's the difference here. So she could actually learn, like, oh, I've decohered. It would seem, okay, Bob must have done his measurement. Okay, that would be a problem, right? Okay. So this is a paradox which has a resolution, or at least it suggests a possible resolution, which it in fact turns out to be the true resolution, which is there would be no paradox if Alice's superposition always decoheres at a constant rate outside of a black hole. And furthermore, if that rate is precisely the rate that you would expect if there were optimally sensitive bobs filling the interior of the black hole, making optimal measurements. Okay, then there would be no paradox, because then the outcome of Alice's interference experiment wouldn't depend on whether or not Bob releases his particle, because the black hole itself is going to decohere her as if Bob had released a particle. So you can conjecture that perhaps outside of a black hole, unlike outside of a cold dead star, perhaps there's some unavoidable rate of decoherence that in a sense is forced upon you by causality. And in fact, that's true. What we showed in some papers over the last couple of years is that outside of a black hole, Alice's coherence is always degraded by an unavoidable flux of entangling gravitons that are emitted and fall into the black hole. And these gravitons are extremely soft. I remember, Alice is going to try to maintain coherence of her superposition. So she's going to do things as adiabatically as possible, just like in the neutron star case. That means that the energy of the gravitons can be made arbitrarily small, because it's just going to scale like the energy will scale like 1 over the time scale she does her experiment in. But the number of gravitons turns out, in the case of the black hole, not to scale with the energy.
Sorry, quick question. So, is there any decoherence if you have a star, no horizon?
So in the case, so there's two. So first of all, it was important that it's a cold dead star, because if you have a star with lots of internal degrees of freedom, you could become entangled with those internal degrees of freedom. And that's just ordinary decoherence. So, but in the case where I cool the star down, so I'm not just getting entangled with the, plasma degrees of freedom of the star, then indeed the effect, there will be no decoherence. Well, the decoherence will be, as long as I do things over a sufficiently long time scale, I can make the decoherence arbitrarily small.
But then we have a little bit of a puzzle, because then Alice, standing outside of this dead star and has no idea whether there's a horizon or not, because horizon is not something that you could observe, it's just something you need to know the future of the evolution up until eternity.
Yes.
And sees either the coherence or doesn't.
Yes.
So what's the problem with that?
Good. Yeah, that's a good point. So in fact, we wrote an entire paper on this question, which the title is The Local Description of Decoherence Due to Black Holes, something like that. That's roughly the title. And the point is that that won't be the point of this talk, but I'll just briefly summarize the answer. Yeah, the space-time looks like identical in Alice's laboratory. So clearly it can't be just like she has no way of learning about the metric all the way over at the horizon. She does her entire experiment, and you could describe her entire experiment as taking place within this causal diamond here. Mm-hmm. And there should be some local explanation of what's going on there. And the point is that outside the vacuum of a quantum field outside of a black hole is very different than the vacuum of a quantum field outside of a cold dead star. And in particular, it has very different low frequency fluctuations. That a black hole effectively rumbles at what looks like a white noise spectrum down at near zero frequency. And in particular, the quadrupole moment of the black hole has a non-zero expected variance in Alice's laboratory, or the quadrupole moment of the vacuum, due to the black hole, has a non-zero variance in Alice's laboratory. That kind of rumbling of the quadrupole moment causes stimulated emission in her lab. So she's has a stimulated emission into modes that preferentially fall into the black hole because of this additional low frequency tail. That tail doesn't make it out to infinity, by the way, which is why, the spectrum looks thermal at infinity, but even at 100 M out, it doesn't look thermal in Alice's lab.
So is the answer that here, our AMO colleagues, if they're patient enough, they can see whether there exists, they can answer definitively whether there are black holes, the horizons in nature out there?
You could tell whether or not, it depends on, so the time scale you need to wait to see the difference between the black hole and a kind of black hole mimicker would basically depend on how long you have to wait before you, if you imagine that the black hole mimicker formed from gravitational collapse, you need to wait until the collapsing, until you see in your past the collapsing shell arrest before crossing the Schwarzschild radius. And as long as it's falling as long as you see it falling in, that process of falling in will also give rise to some low frequency mode. So if it arrests at like a Planck length away or something like that, you'd have to wait an enormously long time. Yeah. And due to this unavoidable emission of entangling soft gravitons through the horizon, any superposed body outside the black hole will decohere after a time given by this formula. The capital D is your distance away from the black hole. Capital M is the mass of the black hole. Little m is the mass of your superposed body, and little d is just the size of the superposition that you made. And this is a very weak effect, and it falls off with distance. But it is a universal source of decoherence outside of black holes. And there's an analogous effect for any charged body outside a black hole due to the superposed Coulomb field as opposed to the superposed Newtonian field, which scales like this. One depends on the quadrupole moment, one depends on the dipole moment of the superposition. And as you might guess, if you thought about this for a little while, there's a directly analogous effect outside of a de Sitter horizon, because the same causal argument would go through outside of a de Sitter horizon. So it shouldn't be too surprising that you also get an unavoidable rate of decoherence due to our de Sitter-like horizon here in our universe. But again, it's very small, so I unfortunately wouldn't. I wouldn't expect. I think the rate was something like, if I took if I replaced the sun by a black hole and superposed the Earth by its entire radius, then it would decohere in 10 microseconds. But to make such a superposition would be incredibly difficult.
In principle, that temperature depends only on two parameters, right? So you have three length. There's Planck length, there is the D, and then there's capital D.
Yeah.
You should just a function of those numbers in Planck units, right?
Yeah.
That will give you the intuitive way of thinking about it.
Yeah. That's right. And sorry, this is a time, not a temperature. But,
oh, sorry.
But yes, exactly. Yeah. Good. So, oops, sorry. So that was a lightning review of some work that's taken place over the last couple of years, because I wanted to motivate, what I'm going to tell you about in this talk. We relied, actually, I think Nima kind of anticipated what I was going to say here, but we relied on the presence of the horizon to reason about this phenomenon. And you could say, what would Alice blame for her decoherence if she knew nothing except what was going on in her laboratory? And well, the answer is what I was just alluding to a moment ago, which is that I should be able, this is a local quantum field theory or perturbative quantum gravity. It's also a local quantum field theory. I should be able to formulate this just inside the causal region of interest for Alice. And what is responsible for the decoherence in that case? Well, the answer is that this expected value of n gives the number of entangling gravitons that are emitted into the black hole. And as it turns out, one can compute this number of entangling gravitons in two different ways. You can compute it on the horizon, but you can also compute it locally in her laboratory using this formula. And this formula is nothing more than the variance of the metric perturbation in her laboratory. And this delta t is the perturbed stress tensor due to her superposition. And the number of soft gravitons in her lab can be alternatively understood as just a response to the vacuum fluctuations outside of the laboratory or outside of the black hole in her laboratory. In particular, if I take the 2-point function and use it to compute the power spectrum of fluctuations in Alice's laboratory outside the black hole, then that reveals at low frequencies a fluctuating quadrupole moment of the vacuum. And now this is a low frequency expansion. So, this is if I go, there are order omega corrections to this. But at low frequencies, the power spectrum of the quadrupole fluctuations asymptotes to a constant. So the important part of this formula is that this is omega independent. So as that omega goes to 0, this doesn't go to 0, it goes to some non-zero constant, which means that at low frequencies, the black hole in her laboratory looks like it has a fluctuating quadrupole moment. That fluctuating quadrupole moment stimulates the emission of further radiation produced by her superposition that wouldn't be there in the absence of this quadrupole moment. And that is the local description of the decoherence effect, is that the black hole behaves as if it has a fluctuating quadrupole moment. It's quite surprising from a classical point of view, because you would say that a black hole should be just described by, it should be about the simplest thing you could imagine, just described by its mass, angular momentum, and charge. So what is there to fluctuate? Well, that's an interesting question, but the calculation shows indeed the black hole has fluctuating multipole moments in its exterior, despite being such a simple object in the classical description. So good. So we've seen that outside of a cold dead star, you would not get this effect. Outside of a black hole, you do, because of this low frequency behavior of the power spectrum. This raises a natural question of, could a material body produce similar fluctuations in its exterior? What could you mimic this effect in some other way?
Can I?
Yes.
I think I missed one point.
Sure.
So were you saying that under this process, Alice or whoever is this process outside locally, we're describing you're emitting gravitons.
Yes.
And the number of gravitons you emit per frequency, if you take the limit of 0 frequency, is finite.
Yes.
So
Yeah.
Thank you.
That's right.
All right.
I mean, I'm not going to disagree with what you just said, but just a slight, refinement is that the number of gravitons at 0 frequency that kind of the local fluctuations in Alice's lab exhibit this low frequency fluctuations. And therefore, as Alice does her experiment, there's a resulting stimulated emission of a non-zero number of gravitons into those modes.
Thank you.
Yeah. So could you mimic this with a material body? Well, the first thing you might try is, well, I said that a cold dead star wouldn't do this, but perhaps a thermal state, perhaps a thermal state outside of that space-time would do this, right? If I just took the space-time of a cold dead star, but added a thermal population of gravitons or photons outside of it, would you get a similar effect? The answer is no, because a thermal state outside of a cold dead star does not have this type of low energy fluctuation in it. And this is something we showed in a recent paper. However, there was a very nice follow-up by Biggs and Maldacena, in which they analyzed the same question, but considering the internal degrees of freedom of the body. And in that case, for the electromagnetic analog of the effect, so where Alice has a charged superposition, there is it is possible to mimic the effect. So if I took a sufficiently hot chunk of metal, for example, about the same size as the black hole, there would be analogous decoherence outside of it, not due to any causal considerations, but just due to entanglement with the internal degrees of freedom, which I can excite more easily because the thing is already heated up. However, in the gravitational case, this is extremely difficult. As they point out in the paper, if I were to try to mimic this effect using some material body and mimic the decoherence due to gravitons, I would find that the resulting material body wouldn't be something you could construct out of standard model matter, for example. I think, perhaps if you have in mind some more complicated model involving the bound state of D-branes, that might be the kind of thing that would possibly be able to mimic this effect. But it would be something with an enormous shear viscosity is what they ultimately found. Kind of some sort of quantum gravitational matter where the shear viscosity depends on G Newton. Okay.
So, sorry, was this idea in line that, I guess I'm asking a sociological question.
Please, yeah.
So Juan and Anna, they were looking at this because they wanted to just, I guess, follow this ideology, I forget what they call it, the black hole from outside.
The central dogma.
Central dogma.
Yes.
So is this in line with central dogma?
Yes. I mean, my understanding of that one of their primary motivations was to kind of verify that this effect is not inconsistent with the central dogma.
Yeah.
That at least in principle, although maybe you might need bizarre material properties, but still at least there's some way that you could mimic this because the central dogma, just for those who are hearing it the first time, is kind of a slogan. It says that a black hole as viewed from the outside, according to a semi-classical observer, should be the same as an ordinary quantum system. That there shouldn't be some huge, it's called a dogma because it's, not something that's been proved, but it's a working principle that there's plenty of evidence for in certain models. And yeah, so indeed, that was part of the motivation as I understand it. And yeah, this decoherence effect then outside of a black hole, well, you can understand it from the point of view of causality, which is how we originally understood it. But the original argument suggests that we should also be able to understand it in terms of some observer inside the black hole. Or perhaps put another way, in light of this material body discussion, perhaps we should be able to understand it in terms of some degrees of freedom of the black hole. So what I'm going to do with the rest of the talk is try to recast this discussion in a language that's more amenable to it, towards analysis in terms of kind of hypothetical degrees of freedom of the black hole. Or put another way, the hypothetical bobs that you could have shoved inside the black hole in order to deduce the effect in the beginning before we started talking about local vacuum fluctuations or the horizon or whatever.
I can ask, I
Yeah.
apologize for asking so much.
Please, that's great.
Can I think of the following baby picture?
Yeah.
That in the presence of gravity provides a universal sector that anything that talks to anything through gravity.
Yes.
They might not be directly coupled, but they must interact through gravity.
Yes.
And this is the effect we're seeing. This is the decoherence we're seeing. Anything inside the black hole will couple to gravitational waves that will couple anywhere else.
Yeah, I think that is. I think that certain. So from one point of view, that is a completely consistent way of understanding the effect. Is that I can't shield gravity, and there might be bobs inside the black hole. And those bobs, if they were there, they could couple to the long-range gravitational field of everything outside. Then the fact that the black hole, then causality comes in and basically says this kind of interesting addendum to that statement, which is that the black hole had better decohere everything outside as if those bobs were there, regardless of whether they're there or not, to avoid a paradox. Yes. So let's try to analyze this again, but from the point of view of these from Bob in the interior. That was the original thought experiment that led to the not only in this talk, but in actual history, that was the thought experiment that led me to conjecture that there should be such an effect. But we didn't actually use this picture with Bob at any point to do any calculations. So it'd be nice to see if this picture is indeed substantiated at a quantitative level. So, okay, imagine that the experimenter, Bob, is trapped inside the black hole. Of course, eventually he's going to die, but we could imagine the black hole is sufficiently massive that he still has a long time to live before he dies. And we can ask a specific question, which is, what's the probability that by performing one optimal measurement of the superposed metric in the black hole, that he would unambiguously learn which position Alice's superposition is in the outside of the black hole? As it turns out, this question has a specific answer. This operational question has a specific answer in terms of the so-called fidelity between the states of the interior metric. There's a very closely related question, which is related to the trace distance between the metric, between these states. I don't, unless people are really interested, I'm not going to get, I would save till after the talk, the refinement that, distinguishes between the fidelity and the trace distance operationally. But the point here is that if Bob wants to learn unambiguously which state is in the black hole, and by that process, learn which position Alice is in, it's going to be the fidelity or the square root of the fidelity, which determines that probability of success. If he gives, of course, I'm giving him the possibility to perform an optimal measurement. So he's doing the best possible thing he could do in the interior. Then the fidelity will determine how likely he is to learn.
So far, you're dealing with pure states, so by fidelity, do you mean overlap?
Good. So yes, exactly. So there's some subtleties outside of a black hole that there's also radiation going off to null infinity due to the Hawking radiation, whatever. The discussion is much simpler if you just consider this on a Rindler horizon, where the same arguments go forward, in which case the fidelity considered on the entire Rindler horizon is indeed just a pure state overlap between the two. But in a second, I'll go to to a finite time case, in which case it'll become mixed state. Yeah. So we're going to use this operational definition in terms of the fidelity and the probability of an optimal measurement to show that there's actually a precise equivalence between the distinguishability according to interior observers and the decoherence as viewed by Alice in the exterior. And that's going to that's going to elevate this kind of qualitative argument that the decoherence should be as if there's optimal observers, and elevate it to a quantitative statement that in fact it must be the case that the optimal distinguishability that the interior observers see must be equivalent to the amount of decoherence that Alice observes in the outside.
So this is an error correction formulation of it, right?
Yeah, it's an approximate error correction formulation, yes. So we're going to do this by going to the language of quantum channels. The reason for that is just because a quantum channel is the most general physical map on quantum states that you can consider. So it's like a general experiment you might do is a quantum channel. And we're going to model the black hole as a quantum channel as far as its effect on the exterior is concerned. We're going to model the black hole as a quantum channel acting on the state in the exterior. So rho exterior is the state in the exterior, n is the quantum channel that takes the initial state in the exterior and maps it to the final state after Alice does her experiment, and models the effect of the black hole as far as Alice is concerned. For any channel, you can find a complementary channel that models the corresponding effect on the environment. So if I think of a channel, I can always think of a channel as taking, taking my quantum state, coupling it to some environment, doing a joint evolution on the total system, and then tracing out the environment. There's a Steinspring theorem that says I can always model a channel that way. There's therefore always a complementary description where I could ask the question, well, given that I coupled to this environment and evolved my system in this open evolution, what would be the resulting effect on the environment of this joint evolution? Right? How does the environment change under this joint evolution? The so-called complementary channel gives me the answer to that question. So this NC is the complementary channel, complementary to the black hole's effect on the exterior. You can think of then NC as giving me the interior of the black hole. So the kind of the effect of the complementary channel acting on the external state is the internal state, because that's the part of the system that I'm tracing out. That's the environment from Alice's point of view. And what we're going to show is that the decoherence d of n incurred by a quantum channel is always precisely equal to the information carried by the complementary channel in the sense of the distinguishability given by the fidelity that I showed you in the previous slide. So in fact, this is going to be true for any channels, but in the case of the black hole, this is going to show that the decoherence of Alice is always equivalent to the distinguishability of optimal bobs in the interior.
Sorry, this is really the recovery map, right? That you're applying, this NC channel?
Well, no, there is a recovery map involved. So when but the NC channel, the NC channel is the map from so N maps the exterior state to the later exterior state after coupling the black hole. NC maps the exterior state to the resulting interior state.
So in the language of modular theory, this is a recovery map of the modular conjugation. So the PET map is modular conjugation, this map, modular conjugation back.
Okay.
And it's because of the trade-off bound.
Oh, interesting.
You're probably going to say that.
No, there is a, you mean the information disturbance trade-off, the diamond norm thing?
Yeah,
yeah, good, okay. So actually, I'm going to show something. So there is a diamond norm information disturbance trade-off, which I will not mention in this because what we prove is something stronger, which I will show.
Okay, sorry, go ahead.
Uh, okay, so what? Yeah, so I'm going to move fairly quickly through these definitions from the point of view of this talk. Although I'd be happy to spend more time. I really want to advertise the results, and then we can talk offline about the nitty-gritty details, and I'd be happy to. Of course, it's all in the paper as well. But I want you to understand just intuitively what these different quantities are telling us. So I want to define a notion called what we call the channel loss, the notion of the lossiness of a channel. And this is basically saying, given some channel, NC, happens to be the complementary channel, so I call it NC, but it's just given some channel, the channel loss tells you how distinguishable is the result of acting that channel versus a channel that just deletes, that just maps all states onto a fixed state, which would be like a delete channel, in a channel that just takes no information, preserves no information about the incoming state. So lossiness is basically how different is the channel you're handing me from the channel that deletes everything. And the more similar they are, the more lossy the channel is. Then a good notion of the information content of a channel is just kind of 1 minus the lossiness of the channel. So a channel that's not very lossy preserves a lot of information. And then the rest of the stuff in this formula is just normalization to make sure that I wanted the information to vary between 0 and 1. Yes?
Is the information of the channel related to like the coherent information that we talk about?
I don't know. That's a good, you could tell me.
Essentially, it's just this notion that you have some IV channel and you
Yeah.
pass in the state.
Yeah.
And how much of the information of that state is preserved post that channel?
It sounds related. I should say that also, yeah, well, we should talk afterwards and see.
I think
Yeah.
it depends on what's your function now.
Yes, it does. Yeah.
If you take it to be mutual information, S, it becomes that.
Okay. Okay, so for us, it's the Ullmann fidelity.
Oh, okay, all the people.
And the reason is because then it gains this nice operational interpretation, which is the one relevant for decoherence. And yeah. So in particular, in the case of Alice's experiment, good, I'm glad this is ringing bells, we're gonna have to talk. In the case of Alice's experiment, the information encoded or carried by the complementary channel, so the information going into the black hole becomes precisely equal to 1 minus the probability that Bob learns unambiguously which state Alice is in, given an optimal measurement of the interior. So this is why, this is why I claim our definition is, operationally suitable for this question, because it gives this nice operational meaning in the case that we're interested in. And I should also say that, when I say the probability that Bob learns, it could be any ensemble of Bobs, it could be you could put lots of Bobs inside the black hole. I'm considering their joint measurement could just be one optimal measurement. So this is a notion of the information content that goes into the black hole that recovers this nice operational notion that the probability that Bob learns, given an optimal measurement that he takes inside the black hole. Meanwhile, outside, we want a notion of decoherence. The notion of decoherence is just saying that if I act at channel N on the outside, and then allow you to act any optimal recovery channel on that channel, still just in the outside of the black hole, how different is the result of that from the identity channel? So if I say, Alice, the black hole does its thing, acts N on Alice, then R is Alice attempting to do whatever she can locally in her lab to try to recover any coherence she can. After all that, how close is she able to get back to the identity channel, which would have preserved the information completely in the outside? And the decoherence is just 1 minus that, so properly normalized. So decoherence is just what's the unrecoverable loss of the amount of unrecoverable destruction due to the channel that acts on Alice's system. As it turns out, in Alice's experiment, this is precisely equal to the ordinary notion of decoherence that that we've used kind of heuristically in terms of 1 minus the off-diagonal elements of Alice's reduced density matrix. So, this is a nice operationally meaningful notion, but it also happens to recover kind of a more, naive notion of decoherence that you might learn in just 1 minus the size of the off-diagonal elements of the density matrix that's recovered in the special case when we restrict to the Alice and Bob experiment. So we have these two notions that give nice, simple operational formulas when restricted to this particular experiment, but they're phrased in a way that's much more general, so that hopefully they'll be able to apply to a more broad range of scenarios rather than just the specific thought experiment. And in fact, well, they will do that, but perhaps more to the point, these two things we're able to show are actually precisely equal to one another. So this is an information, it's a specific instance of an information disturbance trade-off. I'm calling it an information decoherence trade-off because we're specializing to this case where where there's a nice interpretation in terms of decoherence. And it's a stronger statement than the ordinary statement using the diamond norm. You can recover the diamond norm statement as a kind of as a consequence of this. But this is stronger because it's an exact equality between the disturbance and the information.
Sorry, what is stronger than diamond norm?
So there's there's a very closely related formula where I could write, in the diamond norm, I basically say that there's using the diamond norm, there's an analogous definition for a decoherence and an analogous definition for the information. I would have to, I could write it down, but but then if you formulate it in the diamond norm instead of the fidelity, and you run through a similar type of argument, instead of an equality, you get a bound you get inequalities between them, that one bounds the other from above and below type of statement.
Am I correct with them? My understanding so far is that you insist on fidelity as a measure because you have some sort of one-shot recovery.
Yes. Yes.
Whereas often mutual information asks are infinite shot. But
that's right.
My intuition tells me that the infinite shot implies it. But we could discuss.
Okay.
This.
Yeah. Good.
In finite-dimensional quantum systems.
Good.
Not in infinite dimension.
Good. Yes. Okay. Yeah, we should definitely discuss. Yes. But yes, indeed, motivation here was we actually formulated a lot of these things in terms of the diamond norm first. And then I was dissatisfied because it didn't capture quite the operational meaning. So we kept pushing and found this turned out to be, an equality instead of a bound, which was nice. So what this is saying is that the complete decoherence that eventually arises for Alice outside the black hole, if she maintains her superposition for sufficiently long, implies a kind of maximal entanglement with the complementary system. So from the point of view of the black hole, or from the point of view of the kind of hypothetical bobs or degrees of freedom of the black hole, they're unavoidably driven towards completely distinguishable states at late times, as given by if the decoherence goes to 1 or total decoherence, the information content in terms of this operational one-shot distinguishability also goes to 1, just because the two are equal. So Bob and his friends performing optimal measurements in the black hole can, if Alice waits long enough, can learn precisely the which state Alice is in by performing measurements on the interior. And indeed, at any finite time, there's an analogous effect that takes place, right? Now, you know, in the examples that I gave, I described the entire experiment of Alice, and then we compute some distinguishability according to the entire collection of soft gravitons that are emitted unavoidably from Alice into the black hole. But by rephrasing things in the language of quantum channels, I don't have to consider just the infinite time case where I consider all of the soft gravitons emitted. I could imagine if I stop things at some finite time, what's the distinguishability at that finite time? And because of this, and that would just correspond to a different channel. And because of this equality, for every finite time that you stop things and ask how much decoherence has occurred at this time, how distinguishable are the states of the black hole at the same time? At every finite time, the two are exactly equal. There's an exact equivalence between distinguishability and the decoherence. In fact, what this implies is that if I consider a sequence of channels modeling the effect of the black hole at subsequent times, and the corresponding sequence of complementary channels, the effect on the interior as at subsequent times, the decoherence outside a black hole, and therefore by our equality, the information conveyed into the black hole obey what we kind of cutely call a second law for decoherence. So in the particular case of a black hole, there is an unavoidable, ever increasing amount of decoherence that takes place in the black hole exterior, which is therefore by our equality accompanied by an unavoidable increase in information into the black hole. So, right, there's a kind of just an ever-present marching, you know, of onward, you know, there's an ever increasing march of decoherence outside the black hole, and Bob can always get precisely that much which path information on the interior as quantified in this kind of one-shot sense. And you know that the second law captures that fact. So yeah, just to make sure we understand graphically what this corresponds to. Imagine that this is some cut of the horizon at which I could denote by this affine time coordinate along the horizon v sub c. Then if there's some channel that maps, there's some channel n that maps the effects of the black hole on Alice up until that time. So this dashed line is telling me what time you know, I want to cut off and ask the question, how decohered is Alice at that time? Then you know, I can parameterize the decoherence by some, you know, sequence of channels that march forward according to, you know, this cut. And at any given cut, I could ask, what's the distinguishability, you know, of Bob, or what's the distinguishability according to Bob on the interior, due to the complementary channel that maps the state up until that cut into the corresponding interior region that Bob has access to. And what I showed before is that the two, the decoherence and the distinguishability will be precisely equal. But it would be nice to have a more quantitative description of this equivalence. And so it would be nice if I could actually compute this fidelity. And in particular, I'm going to, well, give a formula to compute the Holevo fidelity between states of the interior as perceived by Bob. The Holevo fidelity is closely related to the Ullmann fidelity. These are two notions of fidelity, but the point is that it's one thing to have it's very nice to have an equivalence between the two. It's even better to have an explicit formula for these quantities. And these quantities are most straightforwardly defined in the infinite dimensional setting in the language of Tomita-Takasaki theory, which is basically just a continuum generalization of certain aspects of quantum information theory. And in that language, this fidelity, which bounds the probability that Bob learns, and in the infinite time case, it becomes equal to the probability that Bob learns. This fidelity is given in terms of an operator, which is called the relative Tomita operator. So, okay. Yeah, how am I doing on time? I think I'm running out of time, right?
5 minutes.
5 minutes?
Yeah,
Okay.
easy.
Yeah. So I think you've already got the main point, but I think, well, for discussions coming up later today, offline, I think the next part will be of interest to Nima, but you guys have already got the main point of the talk. So I want to compute things in this, I want to compute the fidelity in this Tomita-Takasaki theory. All you need to know is that the important thing to do this is this quantity called this operator called the relative Tomita operator. And in particular, I want the relative Tomita operator corresponding to the states sourced by Alice's branches of her superposition. Now, for simplicity, I'm going to describe Alice as sourcing two different coherent states on the horizon. And then I want to compute the relative Tomita operator between these two coherent states. Now, on the horizon, there is a known formula for the relative Tomita operator between coherent states in the case where the coherent states correspond to a classical profile that goes down to 0 on the cut at which I'm cutting off the experiment. So I'm stopping the experiment some finite time. I'm asking about distinguishability at that time. And normally, there's an existing formula from Cassini and friends that gives you the Tomita operator if the cut goes through a region where the classical solution is 0 at that time. Unfortunately for us, we care about the case where Alice's superposition is open at the time that we're interested in. We have Alice holding her superposition open, and we're intersecting, we're saying at that particular time, while her experiment's going on, how decoherent is she? Well, okay, that is in what Cassini calls the hard case, for which there isn't a known formula for the Tomita operator. But we got around that. We find such a formula. The key observation is just that the easy case and the hard case, the case where a field configuration vanishes and a case where the field configuration does not vanish on a particular cut, are related by an overall time-independent shift of the metric on the horizon. Such a shift is called an asymptotic symmetry transformation when performed at infinity. But there's an analogous transformation that can be performed on the horizon of a black hole. And by performing that transformation, you can just relate these two, the easy and the hard case, to one another. And the problem is, in order to implement such a transformation, the corresponding gauge field configurations on the horizon lie outside of the standard Hilbert space of free quantum field theory. So you need to enlarge your Hilbert space somewhat. And then in the enlarged Hilbert space, you model this process. When you do that, you you end up, well, you end up including a whole bunch of ultra low frequency modes into your description of the theory that were not there in the ordinary Fock quantization on the horizon. And you know, well, but however, these modes are quite natural to include from a physical perspective, because they're actually the same modes that are responsible for the stimulated emission of Alice's decoherence in this whole story. So, you know, here I'm motivating this just from a purely mathematical point of view, but this extension of the Hilbert space can also be motivated from a purely physical argument. And the way that the Tomita operator goes once you enlarge the Hilbert space is, well, it's kind of an ugly formula, but I claim that this is the formula for the relative Tomita operator between arbitrary coherent states, regardless of whether they're in the so-called easy or hard case. And by including these asymptotic symmetry transformations that shift the metric, you can do the following. You say, I do an asymptotic symmetry transformation. Then I apply the ordinary Tomita operator that would have applied if I were in the easy case. And then I do an asymptotic symmetry transformation again back to the original field configuration. This is all just at a cartoon. I mean, this is the right formula, but I don't expect you to know what all these things are defined as. I just want you to get the point that by sandwiching the ordinary Tomita operator between these transformations, you arrive at a candidate for a new Tomita operator, which you can then just check satisfies all the defining properties of the Tomita operator, which it does. Yeah.
To see that, all you need to argue is that U hat is a unitary, right?
No. That's not quite enough. No. Yeah, I mean, the way to argue it, you really have to check that this object satisfies the defining property of the Tomita operator. And the way that it does is rather non-trivial, but you do a bunch of algebra.
Let me ask my question separately.
Yeah.
Differently. Does U hat leave your vacuum invariant? It probably doesn't.
That's right. Yeah, it changes.
Complicated.
Yeah, that's right. So good. Here I just included the gory details in case someone really wanted to see them, and I'd be happy to discuss more. But the point is just that by including these asymptotic symmetry transformations, perhaps counterintuitively, I gain this additional quantum information theoretic structure that makes it easy to construct the relative Tomita operator in what was previously known as the hard case. But the point was just to get to the punchline, which is now I can compute the fidelity between these two states in the black hole interior. And you get a nice simple formula for it, where you find that the fidelity is, well, not just some abstractly defined thing, but can be defined in terms of a Klein-Gordon norm of some field configurations on the horizon. Okay, and the point is just that once you've computed the fidelity, you can show that at any finite time you have some distinguishability that increases as time goes on, and it asymptotically approaches the value for the decoherence that I showed at the very beginning of the talk. But at any finite time, it's not quite as distinguishable. And that's understandable because at any finite time, there are local vacuum fluctuations that reduce Bob's certainty about which state of the metric he's measuring. And the longer you allow him to average over those vacuum fluctuations, the more certain he becomes. So, right. I mean, that's basically all I wanted to say. The point, the big picture is just that a black hole will decohere any superposition in its exterior, and that decoherence corresponds to a secular growth of one-shot distinguishability that grows as long as the black hole, as long as the superposition is held open, and in particular, long after the black hole is equilibrated from the initial infalling, any initial infalling burst of radiation due to creating the superposition. There's this secular growth of distinguishability that just continues forever. That distinguishability is in the sense of this one-shot, unambiguous state discrimination that Bob could perform in the interior. And there's a corresponding amount of decoherence that is precisely equal to that distinguishability. That can be quantified, that can be proven abstractly, but then it can be quantified in the language of Tomita-Takasaki theory, and which we've done. And it gives you an interpretation of this effect in terms of these kind of hypothetical degrees of freedom of the black hole, or these bobs that you could imagine in the interior of the black hole. And well, from the point of view of this discussion, those interior degrees of freedom would be best thought of as hypothetical degrees of freedom, useful for reasoning properties of the black hole, as we did in the very beginning, to deduce the effect existed at all. But I'll just leave you with this interesting comment, which, of course, from a semi-classical point of view, a black hole doesn't have degrees of freedom. However, there was once a time when it was understood that that protons and neutrons didn't have real interior degrees of freedom either. As for Gell-Mann, he had very good reasons for initially insisting that quarks are mathematical entities. However, as we now know, those hypothetical degrees of freedom of quarks that are now known as quarks turned out not to be mathematical entities. So it's at least tantalizing to wonder whether the degrees of freedom that appear to be so useful in reasoning properties of black holes might not be, in fact, some real degrees of freedom in a more complete description of black holes, as is the case in a UV complete description that as given by, for instance, string theory. But everything we've said here is purely by reasoning at the semi-classical and low energy level. So I'll just leave you with that tantalizing quote, and I'm happy to take any questions. I appreciate your time.
Yes.
Yeah, quick question. Here, suppose I want to model this effect. Instead of a black hole spacetime, suppose I have some high dimensional brainwave scenario.
Yeah.
Something like that. Then in that case, gravity can access that high dimension. So suppose I can put a bob there.
Yeah.
In that high dimension.
Yeah.
And suppose Alice is living in the visible universe, like our given spacetime. So Alice has this superposition of the two mass states.
Yes.
So in principle, in this case also, Bob should be able to decoher the
Yes.
of Alice.
Yes.
That should work. Right?
Yes. This is something I think it'd be. I've always thought it would be interesting to look into. There should be in brain world scenarios various decoherence effects that should take place that would be analogous to this. I haven't worked out the rates, but yes, because gravity leaks off of the brain. Now you need to. The strength of the effect would depend on what the gravity is coupling to off the brain, or what the geometry is off the brain. But yes, there should be scenarios in which you get analogous effects.
Actually, a related question. Have people looked at double holography case of this?
I don't think so, no.
That would be basically addressing.
Yeah, I
This
think
is
so
a more
too.
concrete way where you do know these degrees of freedom, what they are, right?
Yes. Yes.
All right, any last questions, given the time? Not, let's thank anyone. We should empty the room.